Camps on everyone. Let's start off. Hope everyone has gone through the notes. The last thing that we did was this problem based on thermodynamics and SHM. Let's go ahead. Let's do a few more. So we have a U-shaped pipe here, but the edges are looking like this. This is theta. This is theta, and this thing is filled with liquid till this point. This length is L, this length is L, and this length is L. Now the liquid is disturbed, so you pushed the liquid one side by a small x and then you released it. Right, so initially the liquid is exactly on this edge, okay? It is not in that incline wala thing. It's displaced by x and released. Find the time period. So what will happen? The liquid will come here, so this will push here, so this will oscillate, left and right. It will oscillate, the liquid will just keep going left and right. Rho is the density of the liquid. This is a pipe with uniform cross section. Let's see how you do this. And others, do keep your cams on. How do we handle this? This time ka paper was really tough, so most of you did okay and some of you couldn't do well. So do resolve the paper, see where it went wrong. I know you didn't have enough time for the revision also, but like I said, that paper itself is a revision and you get to learn. So do resolve the paper and that will help you a lot. We will have a paper like that every month. And I think few of you did really well. You scored more than 45. So please maintain the scores. Right? Every exam should maintain that score henceforth. How do we do this? Param? Try. You got the answer already. For some of you, this chapter is already over. If you have actually practiced, you would have realized. So how do we start this? The standard question was this, in a standard question, this pipe used to be vertical. That's a standard mains level question. So I just modified it a bit. So what happens here? if you displace the liquid here by x, so let's say you displace the liquid here by x. I'll just shade it here. So you pushed it this side by x. And when you do this, the liquid will rise on this side also by x, because the volume has to be conserved. So look at from this perspective. That means up to this level, the liquid can balance itself. The problem is this additional liquid. That is what is making this whole thing move. So here I'll just mark this in red here. So this additional liquid here, this additional weight is responsible for the restoring force. So when you push one side by x, the other side will rise up by x. So the difference would be 2x actually. So yeah, then you're done. So what is the restoring force? So F restoring is equal to minus mass into acceleration. So here the restoring force, there are two components here. Rho A x, that is the mass, g sine theta, the tangential component then along the incline, plus rho A x g is equal to, this will be minus rho A 3L acceleration. This is the component of weight along that inclined part. And this guy is the total mass. So this red shaded liquid is actually responsible for pushing the whole liquid. Is this making sense, everyone? So that incline thing will be mg sine theta, na? So if I have to just show that part, this is how it would look. So this would be mg sine theta. This would be mg. This m will be rho area x. That would be the total restoring force which is pushing the whole liquid. Rho gets cancelled everywhere, a gets cancelled everywhere, and this would be g into 1 plus sine theta into x is equal to minus, this would be 3L into acceleration. That's your omega square. 2 pi root over 3L by g 1 plus sine theta. Right, Arya? Why will the area be a by sine theta? God, it's a uniform cross section. Everywhere it is a. You can just ignore this part there. It is just bending basically. I didn't draw it properly. It's a smooth curve. I wrote my here uniform cross section. Why are you changing the area? Don't change the question. If the area is different, you can't use this method to solve. But all clear with this? The standard mains question was when theta was, 90 degrees. That's a standard question. You just have it like this. That was easy to solve. This I just modified a bit. So whenever you push one side of x, you actually get a restoring force, one on the incline and one on the vertical. Any doubts on this? Great. Let's see one more. We have a container. We have a block here. Cube of side of base area A. Side is L. So basically A is equal to L square. Okay. And then let the base area be A1. Density of the block is rho B. Density of the liquid is rho L, and the base area of the container is A2. A2 is greater than A1 and rho liquid is greater than rho B. So the block can float. Now, if you push this block by a small x, find the time period. Find time period for small oscillations. Now, this thing, if you remember, I showed you this as an example problem, but here I modified something. If you guys remember, this was the problem, right, which we did, the first one. Find the time period of oscillations. Here, I didn't talk about area and nothing. Yeah, it's not infinity. What was the catch? So, what was the idea here? Why was this problem different from the previous thing which we did? Think of like this. When you push this block by x inside, the area was A1, so the liquid displaced will be how much? A1 into x. But the problem is when this water rises, now you need to understand two things happened here. You look at from the blocker perspective. So one, you went inside by x. Let me just draw a little more deep. This was the initial volume, okay? So this was the initial volume. Then you pushed it inside by x. That was the x which you pushed. And then on top of it, this thing also went up a bit. This y is the height increased by the liquid. This is the liquid rises up. So two things are happening here. Not only you going inside, but the liquid also rises up. So the block will think it has gone inside not by x, but x plus y. Is that making sense? So because the areas are comparable, when you push the block, the water also rises. Did you ever do this thing? If you have a bucket full of water, if you put the mug inside and try to push it, won't the water overflow? Getting it? So pushing the mug, you're doing two things. One, you're pushing it inside by x, but because of that, the liquid rises by y. So when block goes inside, liquid rises by y. So what is this then? So volume displaced, that would be A1 into X, and this should be A2 minus A1 into Y. Are you getting why it is A2 minus A1? Because the block which is there, the new area of cross section will be the remaining. So if you look at the top view, this is how the picture would look. So the block is in somewhere here. So this is your A1. So liquid will increase in the surrounding area. So the liquid rises in the surrounding area there. So now in our first problem, what we did, A2 was infinity. If you take a very large lake, then you can say y tends to 0. So we ignored this scenario in the first problem when we did. So yeah, then you're done. This is the main idea there. So now if you take the block FBD, this was the initial height, which we don't care anyway. This is X. This is the amount you pushed it inside. But in this process of pushing, the liquid also went up. That is Y. So the net change in buoyant force, remember we're always right, the change in forces, which is rho liquid, area A1, X plus Y into G, and acceleration. Then you'll get it in one step. So this is rho L, A1, X plus, this is A2 minus A1 by A1 into X into G is equal to minus mass, which is rho B L cube into acceleration. We get A is equal to this whole term into X, and that's your omega square. I will leave it to you. You can simplify. Clear with the steps, everyone. So if I have to write it down now, I can write it down. This will be rho liquid by rho B G L cube. This would be A1, A1, A1 will cancel. You'll end up with A2.
Sir,
Yeah.
I think you substituted X instead of Y.
सही बोल रहा. This is A1x by A2 minus A1. Then you end up with A2 minus A1, A1, A1 cancel. A1, A2 by A2 minus A1 into X. So that's your omega square. All clear with this? So that's it. The main thing in the question is to realize when you push the block inside, the liquid also rises up. So the net buoyancy force will be X plus Y ka buoyant force, not only X. So when they give you the base area of the container, you have to be careful with that. So this is again fluid mechanics and SHM, right? So previous one was also fluid mechanics and SHM. This was thermodynamics and SHM. So SHM, right? You can literally bring it anywhere. So let's see one more, and we'll go ahead. We got a table here with a small hole here. So we have a particle mass m. The other part of the string passes through this, and there is a block mass m. Gravity is present, and this particle here is going on a circle to maintain the capital M to be at rest. So this guy is going with some speed. This radius is r. So a ball of mass m is rotating in a circle of radius r. What speed? Not given. The other end is connected to a block passing through a hole. So initially the capital M is at rest. Now what you did, you pulled that block M slightly downward and you released it. So this block M, you pulled it by little and you left it. And the block starts oscillating. Find the time period. Hope the question is clear. So the centrifugal force of that particle is actually balancing this mg initially, and that's why it was at rest. I'm sure you must have seen these kind of questions in circular motion. But here we added an oscillation part to it. Let's get this. So what is the catch? That is something you have to figure out, right? Yeah. I'll give an idea. So listen, when you pull the block down, the radius will decrease. Since the tension passes through the hole, the angular torque about the hole is zero. Therefore, angular momentum of the particle about the hole is conserved. So, MBR, if you decrease the radius, speed will increase. If the speed increases, the centrifugal force mv square by r will increase. If the centrifugal force increases, the block will go up. But if the block goes up, radius will increase. If the radius increases, speed will decrease. If speed decreases, centrifugal force will decrease. The block will again come down. So this will just keep going front and back. So you have to conserve angular momentum. That is the catch. Since you pulled it slightly and since it is passing through the hole, the angular momentum is conserved about the hole. That is the main thing that if you you know how to do it. Now do it. Others didn't even get an idea how to start. There I gave you an idea how to start. Now do it. I'll give you 2-3 minutes. One suggestion would be this: don't take V, take omega. Come on, Advai, let's do it. Let's give it a try. So this is going in a circle. The force will be m omega square r. This is capital Mg. So this was tension. This was tension. So the tension will be simply capital Mg is equal to small m omega square r. This is your initial condition. So we get omega square is mg by small mr. So initially it is rotating with this omega. Great. Now what you did, you pulled the block by x. And let this radius become r minus x. And let this guy rotate with omega dash. Now the centrifugal force will be m omega dash square r minus x. The other side, mg is still there. I'm writing all the forces. I'm not writing any change in forces here. Mg is still there, right? And remember, you pulled this by x, so we will assume acceleration in the direction of x. That is the convention we'll stick to. Perfect. So what is the net restoring force? We are writing equations along the string. Yaad hai? NLM mein we did this thing, net force along the string. So the net force along the string is mg. The one who is trying to stop you is the centrifugal force m omega dash square r minus x. That must be equal to the total mass m plus m into acceleration. Is that equation making sense? Sure. The mg is trying to drag you down and the centrifugal is trying to pull you down. These are the two forces that are acting on the total system of m plus small m. Next thing. So that's your main equation there. What? Then we will say torque about the hole is zero because the tension is passing through the hole. Therefore, angular momentum is conserved. So MVR, so initial angular momentum will be mr omega into r, MVR. This will be m r minus x omega dash r minus x. You can also say mr square into this. So from there you get omega dash is omega r square by r minus x whole square. That's your omega dash. Take this omega dash and put it in this equation. And then since x is very, very small, you can use binomial approximation. 2 pi root over m plus mr. Right, Radhiti. But I think वो capital M है denominator में. You got it. Any doubts on this part here? Please ask me. So one force equation, one angular momentum. You're done. Basically, you got everything you need. Any doubts on this page? After this, you're only left with solving. Anyone not convinced with any particular step here? Please ask me. So when I pulled it by x, the radius has become r minus x. So omega would change. So centrifugal force will change. And why is the torque due to the hole zero? Because the tension is passing through the hole. Nera, Arya, omega is not given, right? You can't give an answer in omega. So that then
सर आपने
substitute
जो
it.
लिखा है वही है.
So you solve it ना. जो लिखा है वही क्या होता है? Exam में you do that only. What is the answer for this question? Whatever my sir taught me. बस खत्म. Life was so easy if you should have done that. This would be minus m omega dash would be this guy, which is omega square r power 4 by r minus x ka whole power 4. That's a big term. Into r minus x is equal to m plus ma. Perfect. mg minus m omega square r power 4. That will be, take out r cube common. We'll get 1 minus x by r whole power 3 is equal to m plus ma. This would be mg minus m omega square r. You can bring it up. It will become 1 minus x by r whole power minus 3. But I know m omega small r is nothing but your capital Mg. That would be Mg minus Mg, and this will become 1 plus 3x by r. Hope you guys remember that binomial approximation there. 1 plus x whole power n is 1 plus nx. Mg cancels off. We get a is equal to minus 3 capital Mg by m plus mr into x. The time period will be 2 pi root over r m plus m by 3 capital Mg. That's your time period. I think you got it, Utsa, but why omega square you have to substitute. All clear with this? So how does this motion exactly look like? In case you're wondering here, I did binomial approximation here. So 1 plus x whole power n, you can write it as 1 plus nx. The motion would look something of this sort. So this was the circle. So this will have a small oscillations like this. So there's a technical name called perturbations, Perturbations, perturbations or something. I don't know how to pronounce that. So this is how it would oscillate. So it have a very small oscillations there. So it doesn't go exactly in a circle, but again, since x is very, very small, you can assume it to be a circle. So yeah, it's like a circular motion with a small oscillations. Something of that sort, but yeah. This is the motion of the particle. So it goes in a circular motion with small swings. X has to be smaller. If x is not small, this will become an oscillatory motion. You cannot solve for the time period. All got this? There, circular motion, angular momentum, SHM. So this is what I was saying. SHM is a really good one. So it literally covers everything. Clear with this? So till now what we have done, right, is called a linear SHM. Shauna, can you keep your cam on? Next thing. Angular SHM. Again, mathematically, they're exactly the same stuff what we did in previously. So the previous thing, right, whatever we did, the system was going in a straight line. So we call it linear SHM. So here, the restoring torque. So there it was the restoring force. Is proportional to angular displacement from the mean position. Right? So if you look at the equations, they look identical. Torque is proportional to minus theta. There, F is proportional to minus x. Right? And then we write torque is equal to minus k theta, and then you say this is I alpha. And then we got alpha is equal to minus k by I into theta. And then we said this is your omega square. So we can write this thing as d square theta by dt square is equal to minus omega square theta. So if you see here, it is the same stuff here. So we got f is equal to minus kx. Then we wrote this thing m into a is equal to minus kx. A is equal to minus k by m into x. And we wrote this thing as d square xy. So if at all they ask you something based on the equations, right, you can replace this with x and you can just solve it. So here the general equation was x is equal to a sine omega t plus phi. Here the general equation will be theta is equal to some theta naught sine omega t plus phi. So Max really doesn't care whether you're going in a, an arc or you're going in this thing. This is how the motion would be. So if you take a pendulum, this is your mean position. This is your theta, and the torque is this. So you're talking about that theta there. So mathematically, everything you did in the equation part in the beginning, you can use it here. So there'll be no difference as such. Just replace, theta with x and you'll get everything. So just to write down the general equation there. So theta is equal to theta naught sine omega t plus phi. So theta naught here is your angular amplitude. So we just put an angular word for everything. So what is the amplitude? The maximum displacement from the mean position. What is the angular amplitude? The maximum angle from the mean position. Now, the only problem, right, that I feel here when you differentiate this, you get an omega. But already we used omega in the equation there. So you have to be a little careful there. So I won't call it omega. I'll simply call it angular velocity is d theta by dt, which is equal to theta naught. This is omega. This is actually angular frequency. Omega cos omega t plus phi. So be careful with that. If they ask you find the maximum angular velocity, it is something else. So this omega here is called angular frequency. And if you look at this term here, this is your maximum angular velocity. I hope you remember what is the maximum velocity का formula? A omega. Remember? So A का place में theta naught, and that omega was angular frequency. So I have seen people doing this. They write omega is equal to theta naught omega, and then they get confused. So just be careful with that. There's nothing tough on that, but the terminology is a messed up thing. So we will call it maximum angular velocity. Similarly, if you differentiate again, we get angular acceleration. So at any point of time, if they try to ask you questions, based on the equations or something, I would convert theta into x, I'll solve the problem and bring it back. It works. Max really doesn't care. Like, what do you want to call it? So theta naught omega square is your maximum angular acceleration. So when the pendulum is oscillating, if they ask you find the maximum angular velocity of the pendulum, it is theta naught omega. Theta naught is the maximum angle from the mean position and omega is the angular frequency. Clear with this? So this is a bit about equation, so we'll not go too deep into it. It is the same stuff what we did in the first two classes. Now, in this, we have two special things. One is your simple pendulum and your compound pendulum. Let's see that. So in a simple pendulum, what you do, you take a point particle, mass m, length L. So when it is displaced by an angle theta, again, remember the convention. If you're displaced by theta, alpha also has to be in the same direction. This would be your mg sine theta. Do you guys remember the steps when we did for SHM? Same story. Step 1, choose your system. Step 2, sit straight everyone. Don't put your hand on the head. Step 1, choose your system. Step 2, find the restoring torque on the system. Step 3, find torque is equal to I alpha. Step 4, compare alpha is equal to minus omega square theta. The idea is the same here. L is the length of the string. This over here is the point of suspension. This is actually the length from point of suspension to the center of mass. So when you take the torque here, torque will be mg sine theta into L. That is equal to minus I alpha because you took alpha in the other direction. This will be mg sine theta L. It's a particle, so it is ml square alpha. So alpha is minus g by L sine theta. This is not SHM. This is actually oscillatory motion. But then if you say if theta is small, then we can write sine theta radians is approximately theta radian. So be careful. What is sine 2 degrees? It's not 2. Getting it? Sine can't be greater than 1. So be careful. Convert this into radians. So 2 into radians will be pi by 180. So that is approximately equal to pi by 90. That is the meaning of it. So if theta is small, then you can do this. Then your equation becomes alpha is equal to minus g by L theta. Then that's your omega square. So only for small angles, you can assume it to be an SHM. So that is also an approximation actually. And then you get your formula. Time period is equal to 2 pi root over L by G. And I'm sure you know this formula. We have used this in units and dimensions and errors and everywhere. This is where you actually get it from. Clear with this? But there is a better formula than this. So what if the pendulum is really long? This is a standard question. An infinite pendulum. It's been asked also before in mains and bits and stuff, but let's see what it is. Now, when you take a small pendulum, when you say small pendulum, the length of the string is small. This is what you notice. So the length of the pendulum is much, much smaller than r. R is the radius of the planet. So when you take a string of 1 or 2 meters, it's very small compared to the radius. Now see what happens. When you displace this, the mg is acting downward. Here also mg is acting downward, so there is no problem. This is what we derived it for. But if the length of the string is very large, long pendulum, again, an hypothetical case, but yeah, the L is comparable to radius. So we have a long pendulum here, and the planet looks like this now. You're getting it? So that's your planet there. And that's a very long pendulum there. We are still assuming it is pretty close to the surface, okay? L is comparable to R and particle is very close to the surface. So the G is still constant. Now see what is the problem. When you displace this by theta, again I'm exaggerating the figure here. This mg will be this way towards the center of the planet. This mg will be this way towards the center of the planet. Can you see the difference? Do you really think in both the cases you'll get the same answer? Here both are acting literally straight, and this thing you can see how mg has turned actually. So the idea is this: when you take small pendulums, you can treat Earth as a flat surface. But when you take long pendulums, the Earth ka curvature also comes into the picture. Clear the difference? Why it will matter? So the radius of the planet will actually start mattering now because of that curvature. So how do we solve this? Now, if they ask you to find the time period for a long pendulum, that would be a really good advanced level question. So let's derive this for a long pendulum. But that final result, right, which I'm going to give you, is needed. All hypothetical cases, right? Physics mein whatever I taught you till now, 90% was hypothetical. It's just to, the concepts and stuff. Okay. I'll just exaggerate the figure a bit. So let this thing rotate by theta. Understand this is also pretty close to the Earth. Let this angle be phi. Okay. Mg will be acting towards this. So what you want to find is this component here. For the restoring force, you need a component perpendicular to the string here. So this would be 90. And how do we get that angle? So you can just make a small triangle there. You will see. I'll name these points. I'll call it O. I'll call it C. So this is O. This is C. This is that particle M. This was angle theta. This was angle phi, and this angle will be 180 minus theta plus phi. Wait, let this be beta. So I want to find that only, anyway. So that would be 90 plus beta. So theta plus phi plus 90 plus beta is 180. So we get beta is 90 minus theta plus phi. Perfect. So what's the restoring force here? So the torque is mg. The component of that will be cos beta. That's your restoring torque is equal to minus I alpha. That would be sine theta plus alpha, theta plus phi. I is nothing but ml square because it's a small particle. Now for small angles, we can say theta plus phi is theta plus phi, but I want alpha in terms of theta, not in terms of theta plus phi. So there is one more approximation here. So when this guy rotated theta, and this arc length will be L theta. From the center, when this rotated by phi, this arc length will be R phi. Since it is a very small displacement, I can make an approximation L theta is equal to R phi. The arc length will remain same. So from here, you'll get phi is equal to L by R theta. Now again, for small angles, this will become mg theta plus phi will be L by R theta is equal to ml square alpha. We end up with alpha is equal to minus g by, there's an L also here.
Sir, also in the step before it.
अबे बेकार आएगा. Therefore, the time period is given by 2 pi root over 1 by g into 1 by L plus 1 by R, where R is the radius of the planet. That's your time period there. So remember, when you take the torque, you need mg component perpendicular to the string, isn't it? So we need that mg cos beta. But how do you get beta? So from the triangle, we can get beta in terms of theta and phi. So if you displace by theta, alpha should be proportional to theta. This is alpha and this is theta. But you got alpha in terms of theta plus phi. So somehow I need to eliminate phi and get theta there. That will come from this arc length ka concept. When you displace it, you can assume it to be almost a circle, and then arc length from the top and the bottom must be equal. So this is your general formula there, and you should know your derivations. Any doubts on this? How did I get beta? That is one. How did I get theta and phi correlation? That's it. These are the two main things. Once you got this, the rest of the things will follow. Now, this formula, right? I would strongly recommend you remember this. 1 by L plus 1 by R. Now, look at this formula here. If your radius is much, much greater than L, basically it is your short pendulum. Then 1 by R will tend to 0 because the radius is very, very big. Then your time period becomes 2 pi root over L by G. This is the first formula which we derived. But if the length is much, much greater than R, right? This is also called as an infinite pendulum. And this result, you should definitely remember this. This thing even came in NEET exam also. It came in NEET, it came in mains, it came in bits. I think it must have popped multiple times. And most common mistake people do is this. They think 2 pi root or L by G, since length is infinity, time period is infinity. So in this case, 1 by L will tend to 0. Then your time period becomes 2 pi root over R by G, where R is the radius of the planet. That should definitely remember for a mains or a bits level exam. But this result is important. Could be an advanced single choice question. Or they will say if L is equal to R, find the time period. You're done. Most people won't have a clue how to start. Clear with this. So that's a long pendulum there. All clear with this? So that's about the simple pendulum, when you have a point particle with a string. The next one is your physical pendulum. Physical pendulum, compound pendulum, yeah, you can call it. So in a physical pendulum, the difference is instead of a particle, we keep a full body hanging. Think of your calendar. Your calendar is hinged. So we are hinging here. So your center of mass is somewhere here. Idea is the same. This is theta, this is mg, and this d. D is the distance between the hinge and the center of mass. We get torque is equal to mg d sine theta is equal to minus I hinge alpha. So for small angles, it will become mgd by I hinge theta. Therefore, the time period is 2 pi root over I about the hinge by mgd. So whenever you're having a body instead of a point particle, we have to use this. For a particle, I will be ml square, md square, dd will cancel again, you get root L by G. So just to show an example, imagine you take a disk, MR, and you suspend it here. How is this? Look into my screen. So if you can see this book, so the disk is rotating like this. Can you see how it is going? It's like your calendar on the wall. So if you see the topmost point here, this is the hinge. Axis is into the plane. So, and this guy is just swinging here. So if you want to find the time period for this guy, so this is your COM. This is R. So you want to find I about the hinge. What is I about the hinge? For a disk, mr square by 2 plus mr square, 3mr square by 2. Parallax theorem. Therefore, the time period for this system will be 2 pi root over 3 mr square by d2 by mgr. Substitute and you'll get the answer. Easy. So you should know your moment of inertia, you should know your center of mass. And once you know that, substitute and you're done. This is your physical pendulum there. So these are the two things. The simple pendulum, you're attaching a point particle. So center of mass will be the point particle only. In a physical pendulum, you're taking a rigid body, maybe a bigger one. So center of mass will matter. Any doubt so far? So that's about your angular SHM. Primarily, that's it. There's only two things you have. And then let's see a few more models there. Any doubts? Anyone not clear with any particular thing so far? Please ask. The simple pendulum, the infinite pendulum, or the physical pendulum. Clear? Great. Let's see some questions then. Mass m, length L, this is a string. Now, exactly below this point of suspension here, you kept a nail. Smooth nail at a distance of L by 2. And now if you release this pendulum from here, theta, what will happen? This guy will swing, right? And once it reaches this vertical here, it will become like this. So the nail will block the string and it will oscillate from here. Find the time period. You guys remember we did a question like this in work power energy. Where should the nail be placed so that it will complete a vertical circular motion? So here the pendulum, the string hits the nail and it oscillates about it. Small theta. You can take this angle to be alpha, find time period and maximum alpha. Or you can also say amplitude on the right hand side. So amplitude on the left hand side is theta, amplitude on the right hand side is alpha. You want to hang pendulums from ISS? Yeah, we can do that. Yeah, that one. This is an easy one. Let's get this everyone. This would be a good mains level question. Seriously, it's taking time. So when you're on the left hand side, you will oscillate from here to here, right? And then you will oscillate here. So basically, it behaves like two different pendulums. Then again, you'll come back here, and then again, you'll go back from here. So on the left hand side, when it oscillates, it behaves as if the length of the string is L. On the right hand side, it behaves as if the time period, right? 2 pi is root over L by 2g, isn't it? If you're hitting the nail, the length of the string has become L by 2. So you will travel here T1 by 4, T1 by 4, and while coming back, you will travel T2 by 4 and T2 by 4. That's it. Therefore, the time period will be pi root L by g, half of this and half of that. We have done this in spring questions, isn't it? You know, this question is like what? ये question याद है? Springs are not attached. It is that exact same question. Instead of springs, you have two pendulums. You do half of that oscillation and half of this oscillation, right? And how do you find alpha? The first thing is to realize if this is the floor, the particle initially is at rest, finally it is at rest. That means initial kinetic energy, final kinetic energy is zero. That means initial potential energy and final potential energy must be equal. So H1 is equal to H2. So when this pendulum goes to the right side, it will go to the same height as the initial one. This angle is alpha, this angle is L by 2, this is L, and this is theta. So this whole vertical length will be L cos theta. And here this length will be L by 2 and this length will be L by 2 cos alpha. Yeah, you just equate the length. So L by 2 plus L by 2 cos alpha must be equal to L cos theta. 1 plus cos alpha is 2 cos theta. Cos alpha is equal to 2 cos theta minus 1. That is the relation between alpha and theta. Clear with this? It's not twice. So the idea here is when you leave it from initial whatever height, the final height will be same. Is that making sense? So H1 is equal to H2 since potential energy must be same. That is the actual relation between them. But yeah, theta is small, so maybe you will have some approximations. Clear with this? Take a break. Come back by 9:40. We'll continue from here. So we have two pendulums here with a spring between them. Both the pendulums are pulled apart and released. Find time period apart slightly, so they didn't stretch it too much, and released. Same question. The better question would be this. What if there is a rubber band? Instead of a spring, we have a rubber band. Same spring constant. Rubber band or elastic thread. So they will use these kind of words. Both are same. They get the time period for both of them.
So they won't collide, right?
Small ray, slightly lekana ray. wrote ना slightly करके लिखा था ना. Why you want them to collide?
Okay, sir.
Why are you so evil basically?
सर वो रबर
Keeping
बैंड
up
भी तो
safe.
छोटा हो सकता है.
T plus 2 KL by M. G. Okay. मेरे हो सकता है G plus 2 KL by M. That is right only. Get the rubber band also. Try. Meaning, just to give an idea, when they say they displaced it, you know what they did? Think of like this. This is theta. This is theta. You displaced both of them by theta. That means how much did the spring actually elongate? Theta is small. I can assume this to be L theta and L theta. So the elongation in the spring is 2L theta. Right? That is the idea there. Now, how do you approach? Step one, take the system, draw your FBD, find the torque is equal to I alpha, and you're done. Idea is the same thing. That looks right, Samyak. Yeah, you got an answer without the spring constant. So, what are the restoring forces here? The spring force will be K into 2L theta. This would be your mg sine theta. So the torque will be mg sine theta into L plus K into 2L theta, perpendicular distance L cos theta, is equal to minus I alpha. Now for small theta, sin theta becomes theta and cos theta becomes 1. And this is a particle, so minus ml square alpha. Yeah, that's your omega square, everyone. So how does the problem change with a rubber band? Remember, what does a rubber band do? Rubber band, when it becomes loose, it cannot push, right? A rubber band, it can pull you, but it cannot push. So that is the main idea there. So if you look at the second part of the problem, this is how it looks. So when you both of them are apart, the rubber band behaves like a stretched spring. So this time period will be T1, which you just derived, 2 pi root over. That's what makes this really good. You have to do that Sprinker problem with the rubber band. But when both of them come towards each other, this rubber band simply becomes loose. There's no tension. So they just behave like regular pendulums. So here the time period T2 will be 2 pi root over L by G, the regular pendulums. Since you're doing half of this and half of that, the time period will be pi root over, so basically T1 by 2 and T2 by 2. Clear with this? So if they ask you the question with the rubber band, first you have to solve the problem with the springs. You don't have an option, and then you have to argue with this. Any doubts on this? So it will do half of each oscillation. So for half oscillation, this is the scenario. Yeah. Next one. This is another standard model. So we have a hollow shell. Filled with liquid. There is a small hole at the bottom and the water leaks. Right? You can treat this as a simple pendulum. That shell is very small compared to the length of the string. This was the actual question. How does the time period vary? And exam options were like this. The time period always increases, time period always decreases, time period will increase and decrease, time period will decrease and increase. बस 4 options था. If you look at this is a classic case, where this is an oscillatory but not periodic. And this is not SHM also. So what are the options? Time period, how does it vary? Increase, decrease, increase and decrease, or decrease and increase? This is a standard model. And when I say standard model, like I said, this will repeat in either mains, BIT, CET, Manipal, Vellore, UG. You have multiple exams. Yeah, mostly not for advanced, but yeah, the other small exams. What do you guys think? Decrease and then increase. So in the formula 2 pi root r L by G, M is not there, so it shouldn't depend on the mass. So yeah, there's a fifth option, time period doesn't change. What is the catch? Look at the shells. So initially it is fully filled, then it decreased a bit, then it has become like this, and finally it is empty. If you look at the centromass of the system, here the COM is here, then the COM is going down, then the COM goes down even more, then the COM starts coming up, and finally COM comes back to the center. So do you remember what is L? L is not the length of the string. L is the distance from the point of suspension to the center of mass. So as the mass is decreasing, the center of mass actually shifts downward. So if you look at the motion of the center of mass, it goes down and comes back to the initial position. So when it is full, it is at the center. When it is empty, it is at the center. Goes down and then comes up. So L increases and decreases. Therefore, time period increases and decreases. That is the idea, that it doesn't depend on the mass, but depends on the position of center of mass. Clear with this? Easy one, but a theoretical question. Next one. We have a rod here, mass M, length L. You are keeping a hinge somewhere here. This is your center of mass, and this distance is x. Find x for minimum time period. So where should I hinge the rod so that the time period for small oscillations is minimum? For different positions you hinge, you get different time periods. Again, what is a rod? Rod is a physical pendulum. Do you remember what is the formula? 2 pi root over I hinge by mgd. D is the distance between the hinge and the center of mass. So this is the formula you have to use in case you don't realize. So 2 pi root over I hinge by mgd. You can put it down. Let's get this, everyone. Shreyan, clear so far? Chalo, so let's give it a try. Yashvi, clear with the question? Try. Why are you so tired today? Chalo, give it a try. Advait, clear so far? Adjust your camera a bit, right? I can't see you, Advait, at all. Nere Baram. Why are you guessing, right? God, solve. You will do like this only in the actual exam also. What? Don't tell me your feelings. Prove it. Okay, let's see. This is more of a math problem. I don't know why you guys are struggling. So what was the formula? Time period is 2 pi root over I hinge by mgd. So what is I hinge? I com, which is ml square by 12 plus mx square. So even your I will change depending on where you're hinging, isn't it? D is nothing but x. Therefore, your time period is 2 pi root over ml square by 12 plus mx square by mgx. So basically, you need to maximize the function inside. So dy dx of L square by 12gx plus x by g, this term must be 0. This will be minus L square by 12x square plus 1 is equal to 0. We get x is equal to plus or minus L by 2 root 3. That's your answer. So there are two answers. You can keep it on either side of the center of mass. This will give you the minimum time period. You know where you get maximum time period? Put it at the center of mass. If you put it at the center of mass, the body will never rotate only. If you displace it, it stays there forever. So time period becomes infinity. Clear with this? So center of mass will give you the maximum time period, and these two positions will give you the minimum time period. So most people, right, they think it is the end of the rod because they think x is big, but you're forgetting even your moment of inertia is getting messed up there. So clear with this? Again, not a tough question, straightforward a mains level question. In a mains level paper out of 25, you will find at least 14 to 15 questions of this level. So let's see one more. Half ring. This is hinged here. Again, just like your calendar, mass and radius are. Find the time period. This is J 2004 ka question. Very old one, but this thing, right? If you remember, we did this thing in rotational mechanics. I told you this will come again. But anyways, let's see how will you do. Again, the formula is the same. 2 pi root over I hinge by mgd. That's it. There's nothing new about the formula. You still have to use the same one. But let's see how will you do this. So this thing is like your calendar again. So this will oscillate left and right. So meaning after some time, it will become like this. Then it will swing like this. It will become like this. So it's swinging left and right. You keep saying it is painful and tough and all. वो JEE में question था वो. You leave it there and come. You have to solve this. It is solvable. You get a pretty good answer in the end.
So it's R by 2 pi or 2R by pi.
क्या है? Neher है सम्यक. You get a really good answer. What are you guys doing? Do it, do it. And interestingly, this question, right? If you do the mistake, you still get the right answer. Okay, let's see. Brute force. But in case you guys remember this, in rotation, this was the question 23. What was the mistake here? What people do? When we use parallaxes theorem, what is the formula? I com plus mdmr square. Where is the center of mass? Center of mass is not the center of the ring. Anyone remembers where is the center of mass for an half ring?
R by 2 pi.
2r, 2r by pi. So this was the thing. This was the question. So when we did there, I told this will come again. So you can check it out. I'll just put it down directly here. There. That's your I about the hinge. And then you're done actually. And what about d here? D is the distance from here. So this is your small d. So when you apply the formula time period 2 pi root over I hinge, which is 2mr square, 1 minus 2 by pi by mgd. D is again r into 1 minus 2 by pi, that gets cancelled. You get 2 pi root over 2r by g. There. You get a pretty good answer. Clear this? Now what some people will do, right? They do this. They think this is center of mass. Okay, and see what happens interesting. If you take that as center of mass, then I about hinge will be, this is mr square plus mr square. So I about hinge will be 2 mr square. So the time period will be 2 pi root over 2 mr square by mgr. You get 2 pi root over 2r by g. You get the same answer. It just happened accidentally, getting it? It's not a rule or something. It doesn't work for a disk or hemisphere. Luckily, it works out here. So if you have done that mistake, two mistakes those are, they would have worked out. It's like operation failed, but patient survived. Happens sometimes. So, but still, it's a blunder. So be careful. Clear with this? It's mostly a rotational mechanics question based on moment of inertia. Next one. This is a good one. We have a rod here, mass m, length L, and we have a disk here. Small m, capital R. So that is the hinge. It is free to rotate. The disk is free to rotate there. So here the disk is stuck. The disk is welded at the center. So there is no hinge there. Right? It's not free to rotate. Find the time period in both the cases. Again, for small oscillations. This is a good one. Let's see how do you handle this. How does your answer change by letting it rotate and by not letting it rotate? Where is this thing from? The first time you encountered something like this was in center of mass. Do you guys remember this? What is translatory motion? What is rotational motion? If every point on the body moves in equal parallel paths, we say it is translatory motion. If every point covers equal angles about the axis, it's called rotational motion. Then we discuss something like this. Ye question yaad hai? If you take a block and if you weld it, and if you take a block and you hinge it at the center, so this is like your giant wheel. And then I asked you this question. In this case 1, case 2, which one is translation, which one is rotation? And if you remember, case 1 is actually rotation because everyone covers equal angles. Look at this orientation here. Huh? ABCD became BCAD. Case 2, if you see, ABCD remained ABCD. This is pure translation. So when you're free to rotate, that thing in the middle doesn't rotate. The second time you encountered this was in rotational mechanics. This you saw in work power energy here. Do you guys remember this question? We have a hollow shell filled with liquid. Case 1, non-viscous liquid. Case 2, it is frozen to ice. And then we argued this way. If you see, since the liquid cannot rotate, the line ABC will always remain ABC. So the liquid is only purely translating. The liquid does not have any rotation. But when it becomes an ice ball, you can see that ABC line is also rotating. Now you also have a rotational component. Is this making sense? So these are the 2 times you have seen this before. This is the 3rd time you're seeing. So you need to have an idea about translation motion and rotational motion. So now if you look at the cases here, now when you are free to rotate, think of like this. So for example, if I take 2 points here, A and B, you know what happens here? When this guy rotates, this line AB will always remain horizontal. The disk does not have any rotation of its own. You're getting it here. The disk is in pure translation. Right? So it can be treated as a point particle. So the moment of inertia of this system, I, will be ml square, capital ML square by 3. This is for the rod. Plus this would be ml square. This is for the disk. And this is only the translation part. Clear with this. So, and what about this? You need to find the center of mass. I think that is the reason someone is saying find put m is equal to m. Right? You can calculate the center of mass position here. So if you take this as origin, this is L by 2 comma 0. So center of mass will be m into L by 2 plus m into L by m plus m. This will be your D. There, you get the time period will be 2 pi root over I about the hinge by D. So everything looks the same. The only difference would be this part. Now in the second part, now you have welded there. If you see the AB part is also rotating, so you get extra ml square plus mr square by 2. So basically you can say like this, the moment of inertia has 2 components. One is the translational component of moment of inertia, like a particle, and another is the rotational thing here. So the disk will get an extra part here now, mr square by 2. So this takes care of translation. This thing takes care of rotation about center of mass. That would be the difference in both the cases, extra mr square by 2. Clear with this difference? So can you tell me which will have more time period? Case A or case B? Whoever has more moment of inertia will have more time period, isn't it? So case B will have more time period. All clear with this question? These are the kind of questions they'll ask in advance. They're not too tough, but if you don't have an idea about the translation and rotation, that if you don't realize in this scenario it is a pure translation and this is a pure rotation, you're gone. Any doubts on this? So instead of a disc, I could have kept a ball, a hollow shell filled with water. I can do the same thing. It is non-viscous water, and then I can say it becomes an ice. You get the exact same logic there. Any doubts on this? Clear with this? So that's one really good one. Let's see one more. Solid cylinder, mass m, radius r. Friction is mu. There is no slipping. We have a spring K attached here. Find the time period for small oscillations and the maximum amplitude. What is the maximum amplitude you can have for SHM? Meaning, just to give a little context here, what is the difference, if you have friction and if you don't have friction? Listen to me. If you look into my screen, you will notice this thing. Suppose if there is no friction, right? If it was smooth, what will happen? The cylinder will simply, the solid cylinder will simply go left and right. This is as good as having like a block. Answer will be 2 pi root or m by k. But if you have friction on the ground, this is how the motion will look. See, you're rotating and going forward, rotating and coming backward. You can understand the difference. If you have no friction on the ground, this guy will simply go left and right. It's like a block and a spring problem. But if you have friction on the ground and if you're not slipping, this will roll forward, this will roll backward, it will roll and go back. So now there is also a rotational part involved. That's the difference when you have no slipping on the ground. Get the time period. Step 1, choose your system. Step 2, displace it by x, draw the FBD, find the acceleration as function of x. Step 3, compare A is equal to minus omega square x. Param, sit straight. Pratyash, adjust your camera a bit. Shreyansh, can't see you. Try. I'll give you another minute and then I'll show you one model. Let's see. Let's displace this by x. Acceleration also will be forward. Write the forces on this thing. What are the forces? The spring force will pull back with kx. Then you'll also have a friction F. You have mg. We have normal reaction. That's it. These are all the forces that you have. Since it is not slipping, you can take the torque about the bottommost point. That's always your safest point. Then torque about A. So another big advantage, right? About A, friction goes off and you don't know the F ka value. There's only one force, kx into R, right? That is the torque is equal to minus I about A into alpha. So we are taking alpha this way. And since it is not slipping here, A is equal to R alpha on the ground. So this would be kxr and IA will be parallax's theorem mr square by 2 plus mr square, 3 mr square by 2 alpha. A is equal to R alpha, so we get A is equal to minus 2kx by 3m. Therefore, time period will be 2 pi root over 3m by 2k. That was the easy thing. And then what about friction here? So F minus kx is equal to mass into acceleration. Newton's second law, just write the force in the horizontal direction. So F will be kx and ma will be minus 2kx by 3. So we get friction is equal to kx by 3. But we know friction ka value cannot exceed mu mg. This will give you the limiting condition. So x must be less than equal to 3 mu mg by k. So you cannot stretch the spring more than this. If you stretch more than this, the block will start skidding. And if it starts skidding, then the friction will start losing energy. This will not be an SHM anymore. Are you clear how to get the amplitude? So time period is still fine. Amplitude is a good one. Yeah, I think most of you did get it. All got this. Let's see one more like this. We have one spring on the top, 2k. We have one spring in the center, k. We have one more spring here, k. This distance is r by 2. Find the time period for small oscillations. You connected 3 springs, one on the top, one in the center, and one below the center at r by 2. What is the catch? Just to give an idea here, let's say you displace it by x. So before that, tell me one thing. If the center is going with speed v, the topmost point is going with what speed? V plus r omega. Since it is not slipping, it is 2v. Make sense? What about the speed of this point then? This point is v minus r omega by 2, which is v by 2. So this is the first thing. All the springs will not compress by the same amount. If the central spring elongates by x, then this point will travel 2x. And this point will travel x by 2. I hope you figured that part first. So if you push this solid sphere by x to the right side, the three springs will have three different compressions and elongations. If you have taken all of them to be x, you're gone. That's the first thing you should have realized. Now can you solve? I'll give you a minute more. 2 pi 8m by 185. Okay. I don't know the answer. Let's see. Seven k by m. Okay, let's see. But I hope this idea was clear. Again, this comes from no slipping condition, rotational mechanics. Every point on that sphere will not move by the same distance. If the center moves by x, the topmost point will go to x. And the point below will go by x by 2. Okay, let's see. So if you draw the FBD, let's say if you move this by x, let the acceleration be a. This spring is pushing with 2k, 2x. This spring is pushing with kx. This spring is pushing with kx by 2. These are the forces, everyone. We will take the torque about the bottommost point. Friction is also there, but it doesn't matter if you take torque about the bottommost point. So torque about A, this will be kx by 2, and remember the height is r by 2. Same direction. This is kx, r. This is a 2k, that's 4kx, 2r. Right? So this is minus IA alpha. IA will be 7 by 5 mr square. Parallaxes theorem. So 2 by 5 mr square plus mr square. How much is this? 4 to 8, 9. 9 plus 1 by 4. 30. 37 by 4. Kx is equal to r. And we know A is equal to r alpha. So this becomes A. These numbers are super bad, right? 37 into 5 by 28 m kx. You guys got the same? Or did I mess up somewhere? Thirty-seven into 5 is how much? 35, 150, 185. I think Samyak got it. Right, Samyak. That's it. The main idea is that the three springs will have different elongations and compressions. Once you got that, it's straightforward after that. It looks like the previous problem. All clear with this? Let's do one more variation of this, and then we'll wrap up for the day. So if you see, all these are rotational based questions, basically. Rotational mechanics based. So we have a solid cylinder. Mass m radius. We have a plank here, spring K. This is a plank of mass m. Same mass, capital M. There is no slipping anywhere. So there's no slipping between the plank and the cylinder. There's no slipping between the cylinder and the floor. Find the time period. Again, these kind of questions, right? There's no standard result or something. You have to go through the process. Step one, choose your system, displays by X. Find the elongations, compressions, whatever are there. Draw the FBD, write the equations, and get A is proportional to X. And then you're done. Like I said, the whole question is actually rotational mechanics. In the end, SHM will come and hijack the problem. Start with this. Let the cylinder move by X. That would be always the best. 11m by 4k. I think सम्या क्यों डिनोमिनेटर में 8 आएगा करेक्ट पर चेक करो. नहीं रे आर्या, that is wrong. That looks right, Ishman. So how do we start? So let's displace this by X, and this will have an acceleration A. Now, can someone tell me how much will the plank move? The plank will go 2x, isn't it? And the acceleration of the plank will be 2a. So if the cylinder moves by A, the plank will go by 2a. Hope you guys realize that. Okay? And then, so this thing comes from the no slipping condition. So yeah, let's draw the FBD of them separately. So if I take the plank, the forces will be kx, k into 2x. There will be some friction between them. Let's call it F1. And this acceleration is 2a. Now, if you take this guy, the cylinder, there will be friction F1 here. There'll be one more friction here, F2. There'll be actually two frictions. And this guy is going with acceleration A and rotating with alpha. Great. So let's write down the equation. So for that one, it is F1 minus 2kx is equal to mass into 2a. That is 1. Since it is not slipping on the floor, I'll take torque about A. At least I can eliminate F2. So torque about A, F2 का torque is gone. This will be F1 into 2R. Now be careful here. F1 का torque is this way, minus K cap is equal to I about A alpha. This is K cap. So directions are important. Till now we just used to put a minus sign, but be careful with the signs. So this is F1 into 2R minus sign. Let's look at here. It's a solid cylinder, so IA will be 3mr square by 2 alpha. Right? Take F1 from here and substitute here. This would be 2kx, 2ma, 2r. A is equal to r alpha. This is 3mar by 2. R goes off, bring all a's together. That would be 8kx is equal to minus 11ma. A is equal to minus 8k by 11mx. Time period is 2 pi root over 11m by 8k. All clear with this? So the most common mistake that I see, people think the Planck is also going with A. So just be careful. Little elongation is double. The acceleration is also double. So that's where things get messed up. All clear with this? I'll give you a few homework questions. So do make sure to try them and come. Thursday when we meet, first thing in the class, we'll be discussing them. So definitely do them. Getting it, these things will take time. So I want you to spend some time before, doing it. So what if we have a spring here? This is a solid sphere. MR. This is a hollow sphere. Right? There's no slipping anywhere. Then what you did, you pulled both the spheres by A and you released them. Now see, I'm not moving each one by A. They're pulled apart by A. Matlab spring ka elongation is A. Find the time period and the amplitude. This would be a really good advanced one. You need to spend some time. So make sure to try this. I'll give you a few more. And amplitude of each sphere. If both are equal, you could have argued it is equal. I'll give you the answer so that if you try, you can verify 2 pi root over 35m by 46k. So that's your answer. So if you got it, then maybe your method is right. So that was one. This is another one. Everything is there. So it's like a spring and a rod and all this stuff. So you should check it out. That's your 39. So this P and Q are like hinges here. So these 2 points will not move. So for small oscillations, we can assume it is rotating about PQ. So just to give a picture again, the picture looks like this. So we have mass m, radius r. So here we have a spring. This is your K1. So basically it is attached there tangentially. Then we have a rod like this. Then we have one more spring like this. So this was the picture there. This was K2, this was P, and this was Q. Getting it? So that spring is attached to that corner there. It's almost tangential. So we have a hinge here, we have a spring here. This is K, and we have a pulley here, and we have a block here. Gravity is there. This is a rod, ML. So the rod is displaced. So find time period for small oscillations. There, make sure to try these 3 questions. Spend some time. You can spend like 10-12 minutes on each question. You can try at least 2 times. Got it? Great. You didn't get it, then anyway, I'll show you in the next class. I was waiting. I know someone will run away. I just want to see who will run away. People are not so smart. Who ran away? Yeah, this guy. Shaunak ran away. Shaunak, are you there? You're not there. Perfect. Great. So do try these questions. We will catch